In this lesson, we're going to look at systems of equations that have unusual solution sets. Normally, when we solve a system, we're looking at equations that if we graphed them would give us graphs that cross at exactly one point. And that one point is the solution. But it is possible to have a system in which the two lines would never cross. In this case, they would be parallel lines, and they're never going to cross, so there would be no solution. And it's also possible to have a system where both equations graph exactly the same line, and in this case the solution is every point that the two lines share. So it's these two situations that we want to look at in this lesson. Let's take the system 4x minus 2y equals 2 and 2x minus y equals 3. Now to solve this, what strikes me at first is that I can make the bottom x term become a negative 4x really easily by multiplying everything by negative 2. But you might also choose to work on the y terms. This is what struck me at first, so I'm going to take the bottom equation and multiply everything by negative 2. Now, my top equation is still the same, and my bottom equation has become negative 4x plus 2y equals negative 6. If I add these two together, the entire left side of the equation becomes 0, and the right side, 2 minus 6, is negative 4. So, since this is a false statement, that tells me that there is no solution to this system. And I know now that because there's no solution, if I were to solve these for y and put them in slope-intercept form and graph them, the two graphs would be parallel lines. Now let's look at 4x equals 3y plus 8 and 12x equals 9y plus 24. If we put these in standard form, where we have x and y both on the left side and the constant on the right, then we can see that we probably want to use the addition method here, and I believe I will try to eliminate the x terms by multiplying this top equation by negative 3. Now I have negative 12x plus 9y equals negative 24, and 12x minus 9y equals positive 24. When I add these together, I get 0 equals 0. Now since this is a true statement, I know that I don't have just parallel lines here. What I have is really two lines that have the same graph. So there is an infinite number of solutions. There are infinitely many solutions, but we can't say all real numbers. A lot of students want to jump here, and they remember when we solved linear equations that when we got something like this, we would say all real numbers. But we can't say that now, because for one thing, our solutions are not numbers, they are ordered pairs. And for another thing, it's not all the ordered pairs that are part of our solution. There are ordered pairs all over the place here that are not part of the solution. For example, the point 0, 0 is not a solution because it's not on these two lines. So there are two ways that we can state the solution here. The solution is all the points that are on the two lines, and so we can say that the solution is the set of all x, y points such that 4x equals 3y plus 8, because remember that was one of our equations. We could also say that it's all the xy points such that 12x equals 9y plus 24, because that is also one of our equations, and the two equations contain exactly the same points, so it doesn't matter which one you use, one of them does the trick. And that is the solution to an infinitely many solutions type of problem.